Hey there, folks. In this video, we're going to take a look at exponents. You worked with exponents a little bit in 6th grade, so we're just going to review what exponents mean and what the notation looks like for those, and then we're also going to practice with some properties of exponents that might be a little bit new for you here on the back side. So what are exponents? Well, exponents are a way to represent repeated multiplication. So for example, if we have 4 times 4 times 4, we can shorten this by saying this is 4 to the third power. Okay, 4 to the third power. So if I were to use a couple of variables, if I were to use an x and an n up here, okay, this the big number, okay, in this case the x, is the base, and then the smaller number up at the right, that is what's called the exponent, the n in this case. So anytime you see something in this form, it again is read as the base, which in this case is x, to the exponent's power. So in that case, that would be the nth power. So that would be read as x to the nth power. Okay, so what we're going to do in this chart below is I'm going to give you what's called expanded notation, and that's just saying that I've written it out in multiplication format, and we're going to write the exponential notation, and then we're going to write the value of the number if possible. So for number 1, 11 times 11, 11 times 11 is 11 squared, and 11 squared is 121. Anytime you have something to the second power, we can also say that's squared. Number 2, we have 2 times 2 times 2 times 2 times 2 times 2 times 2. That's 2 times itself 7 times. 2 times itself 7 times. And if I multiplied 2 by itself 7 times, I would get 128. Okay, 128. Number 3, negative 5 times negative 5 times negative 5 times negative 5. That is negative 5 to the fourth power. Notice how I've written the negative 5 in parentheses. Okay, anytime we're taking a negative power or a negative base to a power, we need to put that negative sign in parentheses. If you take a negative number times itself an even number of times, think about what your sign would be. Negative 5 times negative 5 would be a positive 25. This negative 5 times this negative 5 would be a positive 25. So you would end up taking a positive times a positive. So our answer is going to be positive. You actually get positive 625 when you do that. Number 4, we have 1/4 times 1/4 times 1/4. This is 1/4 to the third power, or 1/4 cubed is how we could say that. We know that 1 times 1 times 1 is going to give us a 1 in the numerator. 4 times 4 is 16, and times another 4 would be 64. So that's 1/64. For number 5, I actually have 2 different bases. So we're going to write this as 2 powers. We have a 7 times 7, which is 7 squared, and a 4 times 4 times 4. 4 times 4 times 4 would be 4 to the third power, or 4 cubed. So I can write this as 7 squared times 4 cubed. 7 squared times 4 cubed would be same thing as 49 times, and then 4 cubed we talked about already up here is 64. When you take 49 times 64, I'm not going to work through this because I know you know how to do 2-digit multiplication, but you end up getting the number 3,136. So that's the value of 7 squared times 4 cubed, 3,136. Okay, same thing for number 6. We have 2 different bases. We have a base of 8, and let's look at how many times that's in this multiplication problem. That's in here once, twice, 3, and 4 times. So that would be 8 to the fourth power. And then we have a negative 2, 1, 2, 3 times. So this in exponential form is 8 to the fourth times negative 2 to the third. Okay, so in order to find the value of that, you have to figure out, first of all, what 8 to the fourth is. And then once you figure out what 8 to the fourth is, you have to figure out what negative 2 to the third power is. I want you to think about for a moment what negative 2 to the third power would be. Think about, is that positive or negative, and what the value is. Okay, so I'll give you a moment to do that. Hopefully you figured out that negative 2 to the third power is negative 8. Negative 2 times negative 2 is positive 4, times negative 2 again is negative 8. And then 8 to the fourth power is actually the number 4096. 4096, which when you take 4096 times negative 8, you can trust me on this, you get negative 32,768. So that's the value of this expression, negative 32,768. For number 7, I have 2/3 times 9 times 2/3 times 9. So 2/3 is in here twice, so that would be 2/3 squared. And 9 is in here twice, so that would be times 9 squared. Well, let's think about what 2/3 squared is. 2/3 squared would be 2/3 times itself, so that would be 4/9. And then 9 squared is 81, so that would be 4/9 times 81. Well, 4/9 times 81, 9 and 81 cancel, and you end up getting just 36. You can also work with exponents when your bases are variables. Okay, so let's look at number 8 here. I have an a times itself 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So that would just be a to the 9th power, a to the 9th power. And because I'm not telling you what a is, there's no value for that. Okay, it's just a to the 9th power. Number 9, we can think of this two different ways. We have an xy times itself 5 times, so I could write that as xy to the 5th power. If you do that, make sure you put parentheses around the xy. Or you can think of the x and the y as two separate bases, like we did up here with 6 and 7. I can think of the x as being times itself 5 times, so that would be x to the 5th power. And then also the y times itself 5 times, so that would be times y to the 5th power. So really, these are both the same thing, x, y in parentheses to the 5th power, or x to the 5th power, y to the 5th power. And again, that has no value because it's all variables. Okay, for number 10, we'll do that. We have 3 different bases here. We have an r 1, 2 times, so that's r squared, times we have an s 1, 2, 3, 4, 5 times, so that's s to the 5th power. And then we have a t 1, 2, 3 times, so that's t cubed, or t to the 3rd power. So this expression is r squared times s to the 5th times t cubed. For number 11, I have k 1, 2, 3, 4, 5, 6 times, so that's k to the 6th, times we have a 9, 1, 2, 3 times, so times 9 cubed. So because we have a 9 in there, we can go ahead and figure out what 9 to the 3rd power is. 9 to the 3rd power would be 9 times 9, which is 81, times 9 again, and that's going to give us 729. So this becomes 729 times k to the 6th. Anytime we're writing a number with a variable power, the number would come first, and then the variable power would come second. This is the same thing as 729 times k to the 6th power. Okay, the last one here, number 12, we have a negative 7 times a negative 7, negative 7 times negative 7, so that's negative 7 squared. Make sure you put your parentheses around that. We have an m times itself 1, 2, 3 times, so that's times m to the 3rd, and then we have an n times itself twice, so that's times n squared. Well, negative 7 times itself is going to give you a positive 49, so your value for this is 49 m to the 3rd power n to the 2nd power, or 49 m cubed n squared. Okay, so moving on to the back side now, we're going to talk about a couple of special exponent properties that I want you to know for this class. And the first one is the zero exponent property. And so this property just says that any number except for 0 raised to the 0 power is equal to 1. Okay, so if I were to take 1 to the 0 power, that would be equal to the number 1. 2 to the 0 power is also equal to the number 1. 3 to the 0 is 1, 4 to the 0 is 1, x to the 0 power, assuming that x itself is not 0, is equal to 1. Okay, so that's the first property I want you to know. Anything to the 0 power is equal to 1. The other property I want you to know is what's called the negative exponent property or negative exponent rule. And that says that if I have x raised to the negative n power, then I can write that as 1 over x to the positive n power. Okay, x to the negative n power equals 1 over positive, or 1 over x to the positive n power. So we're going to practice both those rules now in these examples below. We're going to write each expression using positive exponents only, okay? Positive exponents only, and then evaluate them if possible. So for number 13, we have 5 to the negative 2 power. So we have a negative exponent here, and we want to rewrite this using positive exponents. Our negative exponent rule says that I can rewrite 5 to the negative 2 power as 1 over 5 to the positive 2 power, or 1 over 5 squared. Well, 5 squared is 25, so that means that this answer would be 1 over 25, or 1/25. For 14, we have 9 to the negative 1 power. Using our negative exponent rule, I can rewrite this as 1 over 9 to the positive 1 power. 9 to the positive 1 power is just 9, so this becomes 1/9. 15, 10 to the negative 3rd power. I'll use my rule to rewrite this as 1 over 10 to the positive 3 power, or 1 over 10 cubed. 10 cubed is 10 times 10 times 10. 10 times 10 is 100, and times another 10 is 1,000. So this becomes 1/1000th. 16, this is 2 to the negative 7 power, so I rewrite it as 1 over 2 to the 7th power. 2 to the 7th power is 2 times 2 times 2 times 2 times 2 times 2 times 2. We actually had this on the front side of your notes, example 2, and we said that 2 to the 7th power is 128. So this becomes 1 over 128. So notice that anytime you're taking a whole number to a negative power, you end up getting a fraction as the answer. Okay, each of these answers so far have been fractions, proper fractions. For 17, we have 5 to the negative 4th power times 3 to the negative 2nd power. So because we have two different powers here, two different bases, I need to split this up and do this as two separate parts. So I'm going to rewrite 5 to the negative 4th power as 1 over 5 to the 4th. And then I'll do the same thing for 3 to the negative 2nd power. That becomes 1 over 3 squared. So now, 1 over 5 to the 4th power, well, 5 to the 4th power would be 5 times 5 times 5 times 5, or 25 times 25. And when I do 25 times 25, I get 625. So this becomes 1 over 625 times 1 over 3 squared is just 1 over 9. So we have 1 over 625 times 1/9. So we have two fractions that we're going to multiply together here. 625 times 9 in the denominator is going to give us 5,625. So this becomes 1 over 5625. For number 18, we have three different powers here. So 8 to the negative 3rd power, I'm going to rewrite as 1 over 8 to the positive 3rd power. 10 squared, notice this one does not have a negative exponent, so don't rewrite this as a fraction. 10 squared is just 10 times 10, which is 100, so this becomes 100. And then we have a 4 to the 0 power. Well, we talked about up at the top here that anything to the 0 power is 1, so this is just times 1. So really this problem is 1 over 8 to the 3rd power times 100. Okay, so let's figure out what 8 to the 3rd power is. 8 to the 3rd power would be 8 times 8 times 8, which would be 64 times 8. And 64 times 8 actually gives you 512. So 8 to the 3rd power gives us 500, 1 over 8 to the 3rd power, excuse me, 1 over 8 to the 3rd power is 1 over 512. And then we have a times 100 still, and 100 is a whole number, so I can rewrite that as 100 over 1. So really, we have the fraction now 100 over 512. 100 over 512 will reduce. Think for a moment how we could reduce 100 over 512. Both 100 and 512 are divisible by 4. 4 goes into 125 times, and it will go into 512 128 times. So this actually reduces to the fraction 25 over 128. Okay, we have a few more that we're going to now use variables with. For 19, we have x to the negative ninth power. X to the negative ninth power I can rewrite as 1 over x to the positive ninth power. And because this is a variable, that's all I can do. I can't evaluate any further. So this would be our answer for 19. For 20, this is a to the negative fourth power, a to the negative fourth. So the same thing, I can use my negative exponent rule and rewrite this as 1 over a to the positive fourth power. For 21, I have a few different powers here. I have r to the negative sixth power, which I can rewrite as 1 over r to the sixth. I have s to the 0 power, and remember anything, including variables, to the 0 power is 1, so that's times 1. And then we have t to the 11th power. That's a positive exponent, so that just stays t to the 11th. Anything times 1 is itself, so the 1 here really doesn't matter. The t to the 11th, okay, this is a whole number, so we're going to put that over 1. So really what we're doing is we're multiplying the fraction 1 over r to the 6th times t to the 11th over 1. When we multiply fractions, we multiply straight across. 1 times t to the 11th is just t to the 11th, and r to the 6th times 1 is r to the 6th. So we get the fraction t to the 11th power over r to the 6th power. Okay, our last example. We have 3 to the negative third power. We're going to rewrite that as 1 over 3 to the positive third. M to the negative fourth power we rewrite as 1 over m to the positive fourth. And n to the fifth power, that's already a positive exponent, so I can leave that as n to the fifth. I can put it over 1 though, since it's a whole number. So we're going to multiply everything on the top times and then everything on the bottom. On the top I have 1 times n to the fifth, so that's just n to the fifth. On the bottom we have 3 to the third power. 3 to the third power is 3 times 3 times 3, which is 27. So we get 27 times m to the fourth times 1. That would just be 27 m to the fourth power. So this fraction here is our answer, n to the fifth over 27 m to the fourth. Okay, be sure that was a lot of information over exponents for this video. So be sure if there's anything here that you didn't understand or need me to explain again in class, you ask that question the next time I see you. Until then, folks, have a nice day. You're all wonderful people. Take care.